morning, everyone. My name is Senfeng Guo, and I'm from GNSS Research Center of Wuhan University. On behalf of Dr. Chen Wang, I would like to share with you some of the research progress of aerosphere modeling at Wuhan University and the application of parallel computing technique. Most of this work are attributed to Dr. Chen Wang here. Most of work are attributed to Dr. Chen Wang. Okay, I divided my presentation into 4 parts. Firstly, the basic methodology involved in aerosphere modeling, especially the global aerosphere modeling using the spherical harmonious functions. In the second part, I will move on to the introduction of the aerosphere products at Wuhan University and the software platform we developed. For the third part, we will give special attention on the parallel computing technique for the global aerosphere modeling. Finally, I will conclude with the pilots and future works. As we all know, aerosphere is one of the most significant effects on the GNSS signals, and with dark frequency observations, we can form the famous geometry-free combination in which we can eliminate the non-dispersive terms. And the left terms are what we are interested in today's presentation. We use this mapping function to convert the S-tag to the vertical tag, and using the spherical harmonious functions to describe the global variation of the V-tag. And from this, by combining these two equations, we can estimate the coefficients here and the DCB parameters using the geometry-free combination. Based on the above methodology, we have developed the software platform, in which this software platform can be mainly divided into 2 parts. Firstly is the data processing, and secondly is the surface part. In the first part, the data of dark frequency observations are downloaded from the IGS server, and then we perform the data pre-processing to detect the cycle slip as well as the outliers. With this clean observations, we can form the normal equation. By solving this normal equation, we can get the model coefficients as well as the global aerosphere maps. All these products are written into files and also visualized as figures. This file and figures will then push to another server for the surface part. Now we are going to take a look at some features of our platform. First of all of these data processing are performed automatically, and the data processing is rather rapid since we have adopted the parallel computing technique. Moreover, we have given our special attention on the robustness of this platform, since we may suffer from the connection problem, the software problem, as well as the hardware problems. So we have developed a tool to self-monitoring this platform. Once we have checked that there is some problem with the aerosphere products, we will produce the products and send a short message to the manager. So with this self-monitoring tool, this platform is rather stable and can be run automatically over years. Okay, in this slide we will give the type and the length of the aerosphere products of Wuhan University, in which we have also provided 1 day and 2 days prediction products. Also, there are real-time VTech maps with a latency of only seconds, and the time resolution of this product is up to minutes. All these products can be downloaded from this website, and for the international users, we use this FTP. As an example, here we give the result of the real-time gym of our university. Actually, this product is generated on the spot of NBus, and for more details for the real-time products of Wuhan University, we refer to the presentation tomorrow morning in the real-time section. Okay, in this slide we show the comparison of the VTech maps for the aerosphere analysis centers from about 2000 to today. We can see from this map that for different associated analysis centers, they have a similar RMS, and the variation along the years are mainly due to the level of sun activity. From this map, we can conclude that the IGS products is a rather reliable source for aerosphere information. Here we come to the second part of our presentation. As we all know, there are more and more satellites, GPS, Beidou, Gartner, and QZSS, and GLONASS. Also, there is an increasing number of stations, hundreds to thousands stations nowadays. So, the parallel computing becomes a very important issue in the data processing. And here we have done an experiment to use the multi-thread mechanism to test the time consumption of the data processing. There are two computers involved in this experiment. Firstly, we have a server, and we have used a desktop to do this experiment. The result is showing this figure. The vertical axis is the time consuming in units of minutes, and the horizontal axis is the number of threads. As we can see, when we use only one thread, the performance of the desktop, the red line, the desktop performs better than that of the server. This is because that the desktop has a higher basic frequency, as shown in this as listed here. As the increase of the thread number, we can see the server performs better than that of the desktop. And for the desktop, the optimal number of threads is 4, and for the server, the optimal number of threads is 16. This is consistent with the core number of each computer. With this optimal threads number, we have tested the time consumption for the desktop and the server computer. As for the desktop, it takes about 40 minutes for daily global aerosphere modeling, while for the server computer, it takes only about 10 minutes on average. Based on the above analysis, we have gone one step further to test the distributed parallel computing with 2 servers and 4 desktops. The hardware configuration is the same as we have listed here. Okay. And we can see from this figure, as the increase of the desktop computers, the time involved it takes only 15 minutes with 4 desktops. The similar result can be found with the servers. If we add more servers, we can accelerate the data processing time consumption. Well, if we combine all these computers, the result is the blue line. As we can see, it's not as good as with 2 server computers. This is mainly because that the servers and the desktop are in two different network segments, so the transmission is the data transmission is time consuming. And we have developed the applications of for the controlling of distributed parallel computing for modeling, as shown in this figure. We can just there are involved only 2 steps to do this. Okay, we have also developed the tool for the exchange file edits. There are several functions for this tool, and this tool can be run under the Windows and Linux as well as the Mac computer. This is the features of the software of the tool. Okay, I will conclude with now. We have the gene prediction products as well as the multi-GNS real-time aerosphere products, which will be achieved before this September. And in the future work, we will focus on the real-time 3-dimensional aerosphere tomography. Okay, thanks for your attention.